Good morning, everyone. So today I have come to continue my part which I have left in the previous day. I was talking about the solution chapter of class 12. So today I will be discussing about the factors on which the solubility of the gas in a liquid depends. I had explained up to the effect of temperature, and today I will be discussing about the effect of pressure. So, solubility of a gas in a liquid increases with the increase in pressure. We know that the liquid is soluble. A liquid is more soluble when the pressure is exerted in it. Suppose, as usual, the hydrogen gas, then oxygen gas, all these gases cannot be dissolved in water readily. So we need to apply high atmospheric pressure using low temperature. Depending on the conditions, we can liquefy the hydrogen and oxygen gas. So increasing the pressure, we can liquefy a gas. So this can be explained with various examples. Then so what I've written, consider a gas at a given temperature and pressure P. So first of all, the gas at the very beginning, the gas is stated, the gas is subjected at a pressure P1 in contact with the saturated solution, which is in dynamic equilibrium. So the gas is exerted a pressure P1 with the gas above the solution in a cylinder fitted with a movable piston. The rate at which the molecules of a gas enter the solution is equal to the rate at which the molecules of the dissolved gas leave the solution. Suppose I don't have a piston, so I am using, so let us assume that this is a beaker. So I am applying a piston high into the gas. So suppose a gas is there above, on the above surface a gas is there. So I have to apply a piston, movable piston, so that this piston can apply a pressure on the gas present in the beaker or in the vessel. As I apply the pressure on the piston, so these gases can easily liquefy themselves into a liquid structure. We know that gases are in the gaseous form, so they will get liquefied if I apply the pressure on it. So here the first pressure which I have applied, that is P1. When P1 is applied into it, then the gases turns to liquefy itself. So the rate of dissolution of these gas, suppose assume that some gases are there which are liquefied into this, and when the rate of dissolution of this gas at P1 is equal to the rate of dissolution of the gas leaving the vessel. So this can be stated that the volume of the gas increases. The volume of the gas increases as soon as we apply pressure into it, and this can be shown with the help of a diagram which I am trying to draw in front of you. So suppose a vessel is there. So suppose this is a beaker. So some gases are there in it. A piston is applied into it. This is a movable piston. We can move it upwards and downwards. We can do it like this. So a piston is applied in the gas. So these air bubbles are liquefied. Air bubbles are liquefied. So whenever the piston is applied forcefully, then what happens? This air which is present in this airtight container, the container should be an airtight container, so that nothing should interfere with the inner surface of the container. So when the gas is coming in contact with that piston, what happens? There is a strong intermolecular force of attraction between the upper layer of the liquid and also the gaseous surface which is present in the inside of the vessel. So there is a strong intermolecular force of attraction. Strong intermolecular force of attraction. So as a result of which the gas becomes liquid. So as a result of which the gas becomes liquid. So the effect of pressure in the gas is that when we apply pressure on a gas, then the gas can easily be liquefied. From this we can state an important law will be coming from this, which is the Handbrake's law. So this is derived from this one only. From this statement we can get the Handbrake's law, which is stating as so from the factors affecting the rate of the dissolution of a gas into a liquid state, we can derive the Handbrake's law, which determines the solubility of the gas. Handbrake's law is determining the solubility of the gas. It was stated by William Henry in 1803. The Handbrake's law states that the solubility of the gas is directly proportional to the pressure applied on the gas. So the Handbrake's law states the solubility of a gas in a liquid at a constant temperature. Here the term constant temperature is coming. This is a very important one. The temperature in this case is remaining constant. So at the constant temperature, the solubility of a gas in a liquid at constant temperature is directly proportional to the pressure of the gas in equilibrium. These two terms are very important. If you students skip these two terms, then the law will be not correct. So the constant temperature and equilibrium, these are the two important terms which you have to add in this Handbrake's law. So what does the law state? The solubility of a gas in a liquid at constant temperature is directly proportional to the pressure of the gas in equilibrium with the solution. So at constant temperature, the solubility of the gas is directly proportional such that the gas is at equilibrium. Suppose I have taken one gas. Suppose a gas is there in equilibrium with a saturated solution when the pressure of the gas above the solution is P, and suppose the mole fraction of the gas is X. Suppose I have taken one gas in this vessel. So the pressure on the gas is P. Suppose a pressure P is taken on the gas, and the mole fraction, what do you mean by the term mole fraction? Mole fraction is the ratio of the how much mole of a gas, how much molecules of a gas is present in the solution, and the mole fraction of the gas is X. So we can write down the Handbrake's law can be defined as, I hope that all of you have written this law in your copies, and the Handbrake's law then states that X proportional to P. X proportional to P. This is, all of you know that this is the proportionality sign and proportionality constant. So X proportional to P or P proportional to X. So as the pressure increases, so the mole fraction also increases, and the pressure increases, mole fraction increases, and the solubility of the gas also increasing. So P proportional to X, or P is equal to KH into X. This is the term, this is called proportionality constant. This is the term, this is known as the proportionality constant. If you remove this sign, we know that a term should be added to proportionate, this sign. So this is the proportionality constant. So this is the proportionality constant, and Kh, this proportionality constant is called the Handbrake constant, Handbrake's law constant. The value of this constant is depending on the nature of the gas. It depends on the nature of the gas, and what type of gas is this, it is dependent on that. So the units of proportionality constant, what will be the unit of proportionality constant is ATM or bar or torr. This is the unit of proportionality constant. So this is the unit of this proportionality constant. So what does the Henry's law state? The Henry's law states that when the pressure above the gas is increased, then the gas will be liquefied more easily. So what are the characteristics of this proportionality constant or Henry's law constant? There are some factors or there are some characteristics on which the Henry's law constant is dependent. Conditions of the Henry's law constant. What are the conditions? What are the conditions? The value of Kh, the value of Kh depends on the nature of the gas. The value of Kh depends on the nature of the gas. Then number 2 will be the value of the Henry's law constant depends on temperature. Depends on temperature. Then the value of Kh depends on the solvent. So it depends on the solvent. These are the factors. I have taken 3 factors. These are the factors on which this proportionality constant depends. First of all is the depending on the nature of the gas. This proportionality constant is directly proportional to the nature of the gas. What type of gas is present is in the solution. Suppose I have taken CO2, I have taken H2, I have taken nitrogen. The intrinsic property of these gases are different. CO2 is not equal to the properties of CO2 is carbon dioxide is not equal to hydrogen, and similarly this is not also equal to the nitrogen. So there is a difference in the intrinsic property of the nature of the gas. So depending on this nature, this proportionality constant or the Henry's law constant is depending. So, and also this is depending on the nature of the solvent, in which solvent it is mixing up with. Suppose O2 is mixing up with water and O2 is mixing up with ethanol. So then that Henry's law constant will be differing. So the rate at which they are mixing with the solution and the constant, they will be differing. So this is depending on the value of the solvent, that is in which that particular gas is dissolving, and it is also depending on the temperature. If the temperature is increasing, if we increase the temperature, then what happens? This proportionality constant will also increase. So the Henry's law constant is depending on these 3 factors. So then we will discuss about the validity of the Henry's law constant, on which gases, on which particular gases this Henry's law depends. or Henry's law is applicable. Validity of Henry's law constant. So the validity of the Henry's law is depending upon some factors. There are some factors in which the Henry's law is holding good, and there are some factors in which the Henry's law is not applicable. That is, the Henry's law is not obeyed. So what are the laws? What are the conditions? The law is obeyed by the gases which are soluble in liquids to a lesser extent. Those gases which are soluble in the liquid to a less extent, in those gases this Henry's law is applicable. This law is applicable. For example, NH3 dissolves in water to a greater extent. So Henry's law is not valid in this case. We know that NH3 when dissolved in water, then it forms NH4OH, NH4 plus OH minus. So this is readily dissolved in water. So this Henry's law is not applicable when the NH3 gas is dissolved in water. So the number 2 point, this is an example of where the Henry's law is not obeying. Then number 2, the law is not obeyed by the gases which undergo dissociation or association in solvents. Those gases which undergo dissociation and association, this Henry's law is not applicable for those gases. For example, ACl. For example, ACl. We know that ACl is a very strong acid and it is very easily dissolved in water. We can easily make from concentrated ACl, we can easily make dilute ACl. So ACl readily dissolves in water. So when ACl is hydrochloric acid is dissolved in water, it dissociates to form H plus and Cl minus. So this hydrochloric acid is dissociated into H plus and Cl minus, and also this H plus and Cl minus forms ACl. So this is a both forward reaction is also there, backward reaction also there. So this is a reversible reaction. So in this case, this Henry's law constant is not obeyed. So there are some other factors in which the Henry's law constant is not obeyed. The Henry's law constant is not obeyed in the gases which reacts with the liquid. For example, NH3. So this one also, this is reacting also with the liquid. NH3 dissolves in water to form NH4OH. So this is dissolving in water. So Henry's law is not obeying here. This law is not holding good. This law is not obeyed when the pressure is too high. When the pressure is too high or temperature is too low. This law is not obeying when we are subjecting a gas to liquefy by making such conditions that the pressure is too high and the temperature is too low. So these are the conditions on which the Henry's law is not applicable. This is not applicable. So there are some practical applications of the Henry's law. What are the practical applications of the Henry's law? I will be discussing now the practical applications of the Henry's law. So this Henry's law is necessary for several reasons which we usually see in our practical life. What are the practical applications? Practical applications of Henry's law. For example, we see why some vapors, why some bubbles are coming out when you suppose it is a aerated drinks bottle, suppose it is a thumbs up bottle, thumbs up is there. When we open the sip of the bottle, then what happens? Lots of bubbles. All of you have experienced it in the summer season. I know all of you are taking this aerated drinks. So what happens? The bubbles are coming out. Why the bubbles are coming out? These bubbles are coming out because the carbon dioxide gas which is mixed with that aerated drinks, it gets released. It is escaping as it is finding some space to escape. So this is escaping. So the reason of so this Henry's law is not applicable in this case. There are some practical applications of the Henry's law which I will be discussing afterwards. So I was discussing about the practical applications of Henry's law. So on what conditions this Henry's law is holding good, and this Henry's law, we are not knowing this, we are unknown about that. In our everyday life also this Henry's law is using, we are using this Henry's law. So in our everyday life also we are using this law, and which is affecting our everyday activities. So first of all, the reason for the expulsion of dissolved carbon dioxide gas with a fizzing sound when a soda water bottle is opened. This already I have discussed a few minutes ago. Then the number 2 is the deep sea divers sometimes face a fatal condition known as the bends. This can be explained by the Henry's law. What happens to the deep sea divers? What they are taking in? They are carrying the oxygen cylinders on their back, and so when they are doing the scuba diving under the water, then the oxygen, if they are taking that oxygen at a fast level, then it is colliding with the outer atmospheric pressure and the inner atmospheric pressure, that is the pressure of the oxygen which is in the gas cylinder. So if they come upon the surface of the water, too quickly, then what happens? These two pressures they cannot cope up with, as a result of which this becomes a fatal condition which can lead to the death of that scuba diver. So what happens? So this is also the applications of the Henry's law. So but if the scuba diver can rises up from the deep sea ocean to the surface of the ocean after with a pause and with a certain interval and with this slowly, then what happens? That fatal conditions can be escaped, and that accident can also be escaped. And next one can be at high altitude climbers become more weak and are unable to think clearly. This can be explained by the Henry's law. What happens in the higher altitude? We know that all of you we are going to the hill stations. That in the hill stations, what happens? The atmospheric condition is very low. The oxygen level present in that high altitudes, the amount of oxygen is very low. So what happens? The climbers, those who are going to the Mount Everest for climbing and all this, they are facing some fatal problems. They are not able to cope up with that condition. So what happens to them? Then their thinking level has become paused. Why this is happening? Because in the higher altitudes, what happens? The oxygen level is slower. So this oxygen cannot reach their brain, for which they are unable to think and they become numb. So these all three are the practical applications of the Henry's law. So now I will be discussing another topic, which will be the vapor pressure. So I was going to discuss about the vapor pressure. At constant temperature, the pressure exerted by the vapor in equilibrium with this liquid is called the vapor pressure. At constant temperature, so the temperature should be constant. The pressure exerted by the vapor in equilibrium, so there will be equilibrium. Equilibrium means a state in which the the gaseous substance and which is dissolving in the solution, and also the solution which is going to take that gaseous substance that remains at equilibrium at a stable rate. So at constant temperature, the pressure exerted by the vapor in equilibrium with this liquid is called the vapor pressure. So in which two substances the equilibrium is maintained? The equilibrium is maintained in between the gas, in between the vapor and liquid. So in between these two, the equilibrium is maintained at the constant temperature. These three terms are very important. So equilibrium, if you skip this word temperature and equilibrium, then the whole law will not be correct. So these are the two important terms. So at constant temperature, the pressure exerted by the vapor in equilibrium with its liquid is called the vapor pressure. So what are the factors in this case? Also there are some factors which are affecting the vapor pressure. The factors affecting the vapor pressure of a liquid are the nature of the liquid, what type of liquids these are affecting, on what type of liquids these vapor pressure affecting, these are the nature of the liquid, which liquid are taking place in this solution, in which liquid are taking place. So the liquids, there is very weak intermolecular force of attraction, in that liquid the vapor pressure will be high. So suppose if we heat any liquid and so suppose a gas is dissolved, suppose I have taken this, a gas is dissolved in the liquid, and if we heat it, then the gas will evaporate. And if such type of conditions in happening, so the gas is very weakly bonded with the solution. So the gas is weakly bonded, as a result of which the gas has escaped from the solution by applying a little bit of pressure, so a little bit of heat, sorry. So the nature of the liquid, so this is affecting, so this is depending upon the nature of the liquid. Then temperature is a very important term related to the vapor pressure. Then rapidly I am going to another law which is called the Raoult's law. So before going to that, I am describing the vapor pressure by these two diagrams. Suppose I have taken two beakers, so these two airtight beakers, and applied a piston over it, and here also. So the evaporation, this part will be the vapor and this part will be the liquid. In this case also, this part will be the vapor, this part will be the liquid. So the more the piston is exerted, the more the vapor is converting to liquid. So rapidly going to the another law which is called the Raoult's law. So this Raoult's law is applicable for the gases which are non-volatile. That is, we know the term volatile. Volatile means when we open the gas, then they really comes out of the atmosphere. So this law is applicable for the non-volatile substances. So they are which gases are non-volatile. So this law is applicable for that substances. With this law states that at constant temperature, the vapor pressure of a solution containing a non-volatile solute is equal to the product of the vapor pressure of a pure solvent at the same temperature and mole fraction of the solvent in the solution. So again the term constant temperature is coming. So at constant temperature, what happens? The vapor pressure of a solution containing a non-volatile solute. So here the solute will be non-volatile. So when the temperature is remaining constant, the vapor pressure of a solute containing a non-volatile solute is equal to the product of the vapor pressure of the pure solvent at the same temperature and the mole fraction. So which two products are coming, which two factors are coming? This is mole fraction and vapor pressure. So Raoult's law states that at constant temperature, the vapor pressure of the solution containing non-volatile solute, it is equal to the product of the vapor pressure and the mole fraction. So up to this, and rapidly going up to that Raoult's law, the vapor pressure of the solution is equal to the mole fraction of the solvent of the solution is equal to the mole fraction and the vapor pressure of the pure solvent, that is P is equal to X into P0, x1 into P to the power 0. So this x1 is the mole fraction. So today we have completed the topics. One is vapor pressure and another one is the Raoult's law. In my next classes I will be continuing the Raoult's law and other laws, and some numerical problems I'll be discussing with you. So today up to this, thank you.